Hello, good afternoon, everybody. Welcome to this second online session of the European Society of Biomechanics, which should have been in Milano these days. Instead of that, we are having these sessions at least to award some of our members. No, yesterday, if you remember, we did the student award and the clinical, and today we are going to have the best doctoral thesis. So I'm chairing the session with my colleague Sara, Checa, that is the chair of our scientific communications committee. And for me, it's a pleasure to present this award, the ESB Best Doctoral Thesis in Biomechanics. If you remember, well, if you are here in this session, maybe it's because you have been thinking on applying at certain point of your research, mainly the students. And well, this is one of the, I think, one of the most prestigious awards we have in the society, and is to recognize the development of an outstanding doctoral final thesis that has contributed to the advancement and the improvements in the theory or applications of biomechanics. That is one of the goals of our society. If you remember, last year we changed the rules for being able to apply, and now for applying to this award you need to be at least be member for at least 6 months before, at the time of the submission. And as I said, it's a very good award, one of the most prestigious, and of course the award includes an honorarium of 2,000 euros and a certificate. And a few years ago, I think this is the third time we do this, we had a huge amount of applications for this award, and we realized that, for example, if you had 20 theses, 20 applications, there were more than one that deserved the recognition. So we decided to have 2 runner-ups that also receive a small amount of money and also a certificate. So this year we had 10 applications. I have to say that these 10 applications were really outstanding and really, really good. It makes the reviewers, the reviewers had a difficult task on deciding which was the winner. So first, I would like to thank the reviewers that help us to decide for who this award was going this year. And of course, we have here the awardee, that is Alberto Sensini from M'r Università di Bologna, that wins the award with the thesis Electrospun, Biomaterials and Structures for the Regeneration of Tendons and Ligaments, Development and Biomechanical Validation. And of course, as I told you, we had 10 theses, very good ones, and we also have 2 runner-ups, our colleagues of Antoine Falisse from KU Leuven in Belgium and Mirko Bonfanti from the University College London in UK. We decided that the Antoine and Mirko, they can also show us their work, so we asked them to record a video that will be published in the next weeks in our YouTube channel. So please don't miss that. We will announce it in a newsletter, but of course, have the time to have a look to the YouTube channel. So in the next minutes, Alberto will present his work, and Sara and myself afterwards, we will be happy to ask him any question that will be introduced through the question section on the GoToWebinar in the platform. Okay, so thanks everybody for attending, and Alberto, is now your turn.
Thank you very much. Thank you very much, Professor Pérez and Professor Checa, for this kind introduction. Just a second, let me try to share the screen and my presentation. Okay, perfect. Okay. Let's see. Can you see my screen? Okay.
Yes, perfect.
Perfect. I would also like to try to start the presentation, and then I start also with all the acknowledgements. Okay. Thank you very much, Professor Pérez and Professor Checa, for this kind introduction. I want also to acknowledge all the ESB Council and the reviewers and the awards committee to have decided to award my PhD thesis with such prestigious prize. And I hope also to have the opportunity to acknowledge all of you in person, maybe the next year at the next ESB meeting in Milan. Before start my presentation, I want just to introduce the groups in which I worked and all the collaboration that I did during my PhD. I defended my PhD thesis in mechanics and advanced science of engineering at the University of Bologna in 2019, working in the group of biomechanics of Professor Luca Cristofolini, with the co-supervision of other two professors, Professor Andrea Zucchelli, head of the electrospinning group at the Department of Industrial Engineering at the University of Bologna, and Professor Maria Letizia Focarete, that is the head of the Polymer Science Group and the Department of Chemistry, Giacomo Ciamizza. And moreover, during my PhD, I had also the possibility to spend several short and long research periods and collaborations with two universities in the UK, the University of Portsmouth, under the supervision of Professor Gianluca Tozzi and the co-supervision of Professor Martha Rold and Gordon Bland, and the University of Sheffield under the supervision of Professor Gwendolyn Riley. Moreover, in the last month of my PhD, I was enrolled in the European Fact Open project Magnify, under the supervision of Professor Zucchelli, in which I had the opportunity to start some collaboration and share research period at the University of Groningen with Professor Raffaella Carloni. And moreover, recently I started also a very nice collaboration with Professor Michael Santerre at the University of Delaware in the US, in which I tried to apply mathematical models in order to increase the mechanical biomimicry of our structures. During my thesis, I worked on tendons and ligaments, as we mentioned in the title of my thesis, that are soft tissues, as very well you know, that is made by a complex hierarchical structure made of collagen fibrils that are axially aligned and connected to each other in different levels of aggregation. These complex structures confer to tendons and ligaments not linear mechanical properties that are mainly characterized by the typical not linear 2 region that is due by the progressive stretch and alignment of the collagen fibrils during the application of a load. This complex mix between structure and mechanics make these tissues particularly prone to injuries. And there are, in fact, it's estimated that there are more than 30 million of tendon and ligament injuries worldwide annually. And despite the several surgical techniques that are developed in the past to manage these injuries, the incidence of failure of these surgeries is still often high and with a wide possibility of improvement. Generally, the surgical applications to manage these tissues are two and divided from the metabolic activity of cells and the patients, and for limited lesions and for young patients, generally the regenerative approach is the more suitable, using biological grafts that, however, due to the cellularization process that they need to have before being implanted in human bodies, sometimes lost their mechanical properties, and moreover, if the cellularization process is not carried out effectively, it can also cause the risk of infections to the patients. From the other side, instead, we have the prosthetic approach for elderly people when the lesions are too wide, to be managed in a regenerative way, And so for these injuries, we use a prosthetic approach with prosthetic devices. However, sometimes these prosthetic devices have a lack in biomimicry, in their morphology, and sometimes has higher mechanical properties compared to the surrounding tissues that they have to be gripped and to be fixed. And this can cause, for example, lesion to the surrounding tissues or the insertion of inflammation. For this reason, researchers, mainly in the last 10 years, have started to work in order to find innovative synthetic scaffolds to manage better these injuries and to try to improve the regeneration of these tissues. In particular, among the different techniques that were applied to manage these injuries, the electrospinning is for sure one of the most promising, thanks its possibility to produce nanofibers by stretching polymeric solutions inside high electrostatic fields that are generated between the metallic needle of the syringe pump in which the polymeric solution is stored and a metallic ground collector. By changing the shape and morphology of the collector and making it eventually movement and tuning the process parameters, it is possible to obtain several different nanofibers with different morphologies, ranges of diameters, and arrangements. Similar, for sure, with the fibrils of collagen of our tissues. Just to have an idea, I show you this scanning electron microscopy image in which you can see in the background a mat of randomly arranged nanofibers compared with a grain of dust and a piece of air. So taking into account this background, the main aim of my thesis was to firstly, using the electrospinning technique, optimize different polymeric solutions. From the regenerative point of view, blends of polylactic acids and collagen and pure PLA, or for the prosthetic approach, the nylon 6,6. And then try to use these nanofibers to try to reproduce the whole hierarchical structures and mechanical properties of tendons and ligaments, starting from the fibrils of collagen with our polymeric nanofibers, passing to the fascicles using Electrospun bundles, and then grouping several bundles together with an Electrospun sheath able to mimic the epitenon, epiligament, or the endotenon, endoligament tissue, reproducing so the tertiary fiber bundles or the whole tendon and ligament tissue. And then, of course, characterize them from the morphological, cell viability, and mechanical point of view. So starting with a bottom-up approach, after the optimization of the nanofibers and polymeric solution, I used an electrospinning machine with an eye rotating drum collector with which I aligned the nanofiber spoon along the rotational axis of the drum, producing nanofiber mats that I manually cut in stripes and wrapped up on the drum, obtaining Electrospun bundles with different morphologies. By cutting them from the drum, I can obtain linear bundles like that of axially aligned nanofibers, or by pulling out them from the drum, we can obtain ring-shaped bundles like that of axially aligned nanofibers. From this SCM image, you can see how porous are the structures inside and the nanofibers that actually align with the structure. Here, I show you some images of the nanofibers that I produced. In the top of the slide, you can see the two different blends of polylactic acid and collagen that we developed. In percentages, 75-25 of PLA and collagen and 50-50. And in the bottom part of the slide, the pure PLA and the nylon 6,6 nanofibers. As you can see, all the nanofibers were homogeneous, preferentially axially aligned, and with an average diameter that resulted to be both for the fibers, for the nanofibers and the bundles, also in the same range of the fibrils of collagen and the fascicles of tendons and ligament. Moreover, in collaboration with Dr. Chiara Gualandi, we designed also and we optimized a dedicated cross-linking process for our PLA and collagen nanofibers, because after the cross-linking, the collagen lost its triple helix configuration and becomes soluble in watery environment. And so we optimized this cross-linking process using ADC and NHS that allows us to maintain the shape and the morphologies of the nanofibers also after 7 and 14 days of permanence in physiological environment. Moreover, as you can see here from these gravimetric results on our bundles, in this case the 75-25 blend, you can see that before the cross-linking, just after 48 hours of permanence in PBS, the bundles lost the 96% of their collagen. But after the cross-linking process, the bundles and the nanofibers were able to maintain the collagen inside them even after 14 days of permanence in physiological environment, losing practically 0% of collagen. The scanning electron microscopy images that I showed you until now are a gold standard technique to investigate this electrospun material according to the high resolution of this technique, but they have a big limitation. They doesn't allow to look inside the volume of our scaffolds. And for this reason, in collaboration with Professor Gianluca Tozzi and Dr. Alexander Cao at the University of Portsmouth, we optimized several high-resolution X-ray tomographic protocols in order to study with a submicrometric voxel size the full field morphologies of our bundles, developing also dedicated setups like that allowed us to reduce as much as possible all the artifacts, for example, of micro movements, increasing the overall resolution of our scans. Here are some results of our XCT scans for the two PLA and collagen blends bundles. You can see that the nanofibers are well defined and actually preferentially aligned both in the surface that in the internal volume of the bundles. And after the cross-linking process, what is visible is that the nanofibers maintain their preferential axial alignment and their shape and structure, also in the most internal volume of our bundles. Here you can see some videos of the XCT scans for the 75-25 blend. In the left-hand side before the cross-linking process, which you can see the nanofibers that are actually aligned, and after the cross-linking, in which you can see that the bundles and the nanofibers maintain their shape and morphology. The same was true also for the nylon 6X and the pure PLA bundles and nanofibers that you can see are homogeneous and made of actually aligned nanofibers, both in the surface but also in the internal volume of our bundles. And moreover, tuning the thresholding of the scans, it's possible also to see the most internal nanofibers that are actually aligned to. Here, two videos of a PLA bundle in which you can see that tuning the thresholding is also possible in the right-hand side of the slide. See the most internal nanofibers that are preferentially actually aligned and homogeneous. Moreover, I optimized a dedicated protocol based on the directionality plugin of FIMA-J, in which I have the possibility to study the full field orientation of the nanofibers inside our bundles. So basically taking the different stack of the XCTs that we obtain by of our different bundles and deciding to place at 0 degrees the axial orientation and at 90 degrees the circumferential orientation of the nanofibers, we investigate each slice of each stack of our bundles, and then making the mean and the standard deviation for the different ranges of angles of each scan. And what we can obtain are histograms like that, in which we have in the x-axis the orientation, the different degrees of orientation, and the y-axis the percentages of nanofibers aligned the different degrees. Here, for reason of time, I show you the 75-25 blend as pan in blue and the cross-linked one in yellow. And you can see that basically, the majority of the nanofiber resulted aligned in a range of 0 to 12 degrees with a progressive physiological, let's say, scatter to the circumferential orientation as happens in the tendon and ligament fascicles. Moreover, with these protocols was also possible to see, for example, in this case, that after the cross-linking process, we have a slightly reduction of alignment of the nanofibers, and this because the shrinkage of the nanofibers that occur after the cross-linking. We tested also, in collaboration with the University of Sheffield, with Professor Gwendolyn Riley and Dr. Liam Boyle, the cell proliferation on our polylactic acid and collagen blends in different percentages and before and after the cross-linking. And what you can see from, for example, this fluorescent microscopy image, after 21 days of culture on the 75-25 cross-linked blend, is that you can see in blue here the human fibroblast nuclei stained in blue, that with the cell nuclei that are elongated along the direction of the red nanofibers that you can see in the background. What you see from the cell viability test is that basically after 21 days of culture, the fibroblasts proliferate on all the different blends, showing basically that cells like these materials. And from the other side, also that the cross-linking process doesn't have any toxic effects on the cell's proliferation. We tested also in several studies also the mechanical properties of our bundles using a tensile test consisting in a monotonic ramp to break, immersing the bundles in saline before the test. In these works, we use different strain rates, physiological strain rate to test our bundles. For the regenerative bundles, let's say, we use a 33% of second on strain rate according to the limited cinematic task that a patient can do after a surgery like that during the rehabilitation period. And from the other side, for the nylon 6/6, in order to the fact that our prosthetic device, or thinking to be in future a prosthetic device or a tool for a simulation of tendons and ligaments in vitro, we used 70% on second of strain rate as worst case scenario of failure. And moreover, in order to try to reduce as much as possible the stress concentration between the bundle sand and the grip of the machine, we designed also dedicated caps and grips like that in this slow motion video that allowed us to reduce the stress concentration and break our specimen in the middle of the God's length. Here, the results in terms of stress and strains for the different bundles. In red, you can see the nylon 6/6, in blue, the pure PLA, and the 75-25 cross-linked blend in orange, while the 50-50 cross-linked in green. And in this box, you can see also zoom in the regenerative bundles. Here, you can see also a comparison between the mechanical behavior of human tendon fascicles for Afro-American and Caucasian men reported in literature. And what you can immediately see is that all the different bundles show a not linear two region, similar to the one of tendon and ligament fascicles, with an elastic, stiffer and brittle behavior for the nylon 6/6, and while for the regenerative blend, we have a ductile behavior suitable as safety factor in case of overload of the scaffold in the early stage of regeneration. That for the 75-25 blend showed also levels of stress similar to the one of tendon and ligament fascicles. Here I show you a comparison of the mechanical properties of the different bundles in terms of failure load, failure stress, failure strain, and Young modulus, compared in the green bar with the average values of tendon and ligament fascicles reported in literature. As you can see, for the nylon 6/6, we had higher values of Young modulus and failure stress compared to the test in literature. And for the PLA and collagen blend, we had slightly higher values of strains at failure. But until now, I have shown you how we have decided to reproduce the fibrils of collagen and the fascicles of tendons and ligaments. But of course, this way was already explored in literature by previous studies. But the real challenge of this work was how to try, and also in the electrospinning research field, of course, was how to try to scale up the process and how to try to reproduce the whole hierarchical structures of tendons and ligaments. I tried to answer to this question developing an innovative electrospinning procedure. Here you can see the setup. There is also a dedicated electrospinning machine that we have developed in collaboration with Dr. Yuri Belcari at the University of Bologna, in which you can see that we have placed some bundles of nanofibers actually aligned together inside this electrospinning machine, able to rotate the group of bundles without twist them during the process. And we placed also a flat plate collector behind the bundles. During the electrospinning process, tuning the times of rotation and stasis of this group of bundles, it is possible to produce an electrospun membrane able to carry out the different tasks. For example, the first is the cover the bundles, but also tighten them and reduce and tune the level of porosities inside the whole structure. And moreover, also the possibility to tune the level of randomicity of the nanofibers of the electrospun membrane, from the total random arrangement up to circumferential orientation of the nanofibers. At the end of the process, what we can obtain, in this case, for the linear bundles of PLA, we can obtain hierarchical structures like that, in which we have the electrospun membrane, similar to the epithelium epiligament tissues on the top, and the internal bundles inside. But using instead the ring-shaped bundle that you see before, it was possible also in the case of nylon 6/6 obtain hierarchical structure, two-level, let's say, structure like that, in which we can obtain also looped ends suitable to better fix these structures, for example, in the testing machine or in a bioreactor, or also in the body of the patient to have the surgeons to suture better the extremities. And from the other side, the process were particularly flexible and allowed also to group more hierarchical structures like that together, as in this three-level structure that I show you, in which we have a unit 3 hierarchical scaffolds, for example, obtaining the possibility to reproduce also the tertiary fiber bundles, the endotendon, endoligament tissue, and also the epitendon and epiligament 1. For the innovative process and structures obtained, the University of Bologna patented this structure and process, not only for the regeneration and replacement of tendons and ligaments, but also for the regeneration and replacement of muscle tissue, nervous tissues, and for the production of sensor and actuators. Here you can see some pictures of our structures in which you can see the bundles inside that are actually aligned and strongly grouped together. And in the third level structures, also the hierarchical structure inside are strongly grouped together with the electrospun membrane that resulted homogeneous and is possible to see here made of randomly arranged nanofibers, while the internal bundle resulted, as we said before, made of axially aligned nanofibers. We continued at the University of Portsmouth the multi-scale investigation of our structures. And here you can see the two-level structure of PLA, in which you can see the bundles inside that are strongly grouped together. And zooming inside with the voxel size, you can see also the electrospun nanofibers on the electrospun membrane that is homogeneous, while in the internal bundles, you can see that they are maintain their axial alignment and porosity suitable to better help the cells to filter inside. And of course, this bundle, as we said, are made of axially aligned nanofibers. Here you can see two videos of the two PLA two-level structure, just to see the homogeneity of both of the electrospun membranes and the internal bundles. And we also investigated the two-level and three-level structures of nylon 6/6. Here you can see that the bundles inside for all the two structures result axially aligned and strongly grouped together. the electrospun membranes resulted homogeneous, and even in the internal volume of the structures, the hierarchical structures in the three-level scaffold resulted actually aligned, and the membranes tuning with the thresholding, we can see also the electrospun membranes inside that are homogeneous and made of randomly arranged nanofibers. Moreover, again, the single bundles are made of actually aligned nanofibers. Here, other videos that help maybe you to see the homogeneity of the process and the quiet biomimicry of these structures compared to the natural tissues. And of course, we investigated also, and I investigated also the orientation of the nanofibers in the full volume of the structures and also the electrospun membrane. Here I report the nylon 6,6 structures just for reason of time. We take some ACM images of the electrospun membrane, and then we apply the directionality plugin as previously showed. And here you can see in gray the three-level structures results, and in blue the two-level structure one. You can see that the nanofibers are basically randomly arranged, but with a slightly circumferential orientation of the nanofibers on the membrane, confirming what I said before about the possibility to tune the orientation of the nanofibers on the membrane. Moreover, we also investigate the orientation of the internal bundles and nanofibers in the full volume of the structure, and in this case using the XCT stacks. And you can see also in green the result for the single bundles nanofibers. And you can see that again, the majority of the nanofibers and bundle results actually align inside the structures with a progressive circumferential scatter. We tested also the cell proliferation on these hierarchical structures, of course, in the PLA two-level structure with the University of Sheffield, and seeding human fibroblasts at the top of our structures after 16 days, as you can see from these histological images, in which in purple are showed the fibroblast. You can see that fibroblasts are able to filter inside the structure from the top and start to grow on the nanofibers, elongating their bodies and nuclei in the direction of the nanofibers, as happens in the physiological tissue, similarly in the physiological tissues. And moreover, the fibroblasts were also able to filter growth on the electrospun membrane and slowly filter inside the electrospun membrane from the porosities arriving inside the scaffold. The cell viability test showed also that after 16 days, we have an increase of the total number of cells. In collaboration with in another study, in collaboration with the University of Portsmouth, instead, in collaboration with Professor Marta Roldo, Gordon Blanc, and Dr. Arianna De Mori also, we investigated also the morphological changes of human fibroblasts on polylactic acid and collagen hierarchical structures after the application of static or dynamic culture in bioreactor. And what we saw was quite interestingly that after the dynamic cultures, the cells are able to elongate more their shape, not only in the internal bundles where the nanofibers are, of course, actually aligned, but also on the external membrane that is basically randomly arranged. As you can see from these different images that we acquired with different techniques, such as high-resolution X-ray tomographies, ACM images, histologies, and fluorescent microscopy. We tested also the mechanical properties of the different hierarchical structure with a tensile test, comparing them with the one of single bundles, using, in this case, for the PLA two-level structure, 100% of strain rate, just to reproduce a worst-case scenario failure. And for the hierarchical structure in PLA, we designed these cemented ends in order to better fix them in the testing machine and try to reduce the stress concentration, as you can see from these slow-motion videos. From the other side, we tested also the ring-shaped bundles and two-level structures in nylon 6,6, using 70% on second of strain rate. And what you can see from this slow motion video is in particular for the two-level structure that we developed first dedicated the helical capstan grips to try to reduce as much as possible the stress concentration. And moreover, as you can see from these two videos, you can see how strong is this very thin Electrospun membrane. In fact, in the left-hand side, you can see when the membrane is not optimized, literally the scaffold explodes after the break that occur in the middle of their gauze length. But from the other side, you have to imagine that the membrane is just 100 and a half micron thick. After the optimization of the membrane, when the breaks occur, you can see how the membrane is able to store the energy of the break of the bundles and maintain the shape and morphology of the overall structure. Here are the results of the mechanical properties in terms of loaded strain for the PLA structures and nylon 661. In red, you can see the two-level structures, and in blue, the single bundles are reshaped bundles. And in the box, you can see the zoom in the mechanical properties of the bundles compared with the typical mechanical behavior of the tendon tissue. And you can see that how all the structures show in a nonlinear two regions similar to the one of tendon tissue, while the PLA two-level structures show a ductile behavior similar to the one of the bundles, while instead the nylon 6/6 showed an elastic brittle behavior very similar to the one of typical behavior of tendons and ligaments. Moreover, here you can see I have matched the mechanical properties of the two-level structures and nylon 6/6 structures in terms of failure load, failure stress, failure strain, and Young modulus with the typical average mechanical properties of tendons and ligaments reported in literature. Of course, you can see that the range of mechanical properties of tendons and ligaments are very wide because they change morphology and structures and function. But what you can see that all the structures fall into the range of their mechanical properties, and of course, tuning the process and the scaling up the inserting majority number of bundles and so on, we can also try to reach the dedicated mechanical properties that we want. So concluding, basically during my PhD, I developed this innovative Electrospun hierarchical structure able to simulate the structure and the mechanics of tendons and ligaments, with also the possibility to reproduce potentially every kind of tendon and ligament of the human body. And we show that cells are able to grow on these scaffolds. Moreover, the future task of our work will be have large animal trials in the very next future to test the performance of our scaffolds in vivo and makes numerical models also to obtain in silico models of these structures, for example, for future preoperative planning. And two possible applications also that we are now testing with the encouraging preliminary results are the nerve regeneration and also the production of artificial muscles for soft robotic application in the context of the European project Magnifying, which I'm working as postdoc, in which we will apply using innovative materials to apply this hierarchical structure to mimic the mechanics, the hierarchical morphologies of skeletal muscle, but also the mechanism of contraction using innovative materials. So with this, I conclude my presentation. I was just before ending to acknowledge all the people that worked with me during this year and are working with me, both in Italy at the University of Bologna and in the other university which I am working. And of course, all the bachelor and master students that during these years have helped me and are helping me to reach these results. And so this I conclude, and thank you for your attention.
Well, thank you very much, Alberto. Now that I remember the thesis, I knew why you win.
Yeah. Good. So thanks also from my side. Yeah, great job. So now to all people participating, you have the chance to make questions to Alberto. If you can post them in the questions box, I will try to forward that. So I will start with some questions. So you nicely show how you can scale up from the 905 to the 3D structure.
Yeah.
I was wondering how large can you go? So how large are your structures? Can you think of a scaffold that really replaces the whole ligament or tendon, or is it limited to?
Okay. Okay. No, the nice stuff of this procedure is that is really scalable, and so potentially we can reach every kind of structure, level of cross-sectional area, and level of arrangement of the different structures of tendons and ligaments that we need. So basically, we can go through, for example, Achilles tendons to crossed ligament, anterior crossed ligament, or even also thinner tendon, as you want. And also concerning the length, we can obtain each length of our scaffold and structures. And so I think it's quite flexible technique.
Okay, thanks. I have a question from one of the participants. The question is, what would be the main next steps to bring this to the clinic?
Okay. The next steps is for sure the first one is investigate in vivo these structures, and we are planned to have hopefully COVID permitting before the end of this year start with large animal trial on sheep to test their performance in vivo. And then hopefully, if everything goes good, we will start also to surgery, to veterinary application of these structures before, to have a large number of cases before and test better their performance in vivo, and then start maybe for custom implants if everything goes good in the next years, also to human patients.
What would be the first clinical application?
The first clinical application we are thinking to be for veterinary one, so regeneration or substitution of ligament and tendons on animals, small animals, for example, dogs, cats, but also scale up on higher animals, hopefully in the future, for example, horses, let's say, and then go to the human one.
Okay. Another question from the participants is, how would this be performing after sterilization?
Okay, we are starting also to investigate this point. We have a slightly reduction, of course, of the mechanical properties, but we are also working, playing with different levels of sterilization and sterilization technique to investigate the best level, for example, of gamma ray radiations or other techniques to reduce as much as possible this loss that is normal for polymeric materials, but also tuning the process parameter, we are able to align more or less the nanofibers, and so the overall mechanical properties of the structure can increase, and so after the sterilization we can reduce this loss basically.
Okay. Good. Another question from the participants regarding the biodegradability of the PLLA.
Yeah.
Did you think into that?
Yeah, of course, we tested the PLA as a preliminary material. The PLA has a quite long-term degradation in vivo. We are thinking about 6-8 months generally in literature, so maybe the times have to be basically that, but of course this structure, as you see, it's quite flexible. So now we have defined a proper structure, but nothing, everything is open. So basically we can also change materials, change polymers, try to test new regenerative materials to produce our nanofibers, and so changing also and adapting also for future application the levels of degradation of our scaffold to, for example, the age of the patient, the level of lesion also that have to be replaced, and so on.
One question here, Alberto, about the biodegradation. You say, well, PLLA, of course, it has a long-term degradation, but
Yeah.
I think you haven't analyzed that, no? The degradation that maybe due to also for if you are doing a fatigue testing, no, tensile and compression, no, fatigue testing on that. If have you observed if there is an increase in the velocity of the degradation, also additionally to put in within cells and with PBS, probably that.
Okay, basically we tested the degradation and the permanence in PBS for our scaffold at the moment up to following also the degradation process and so on, up to 14 days. And what we saw basically was that the main problem was the loss of collagen, because the PLA more or less maintained doesn't degrade too much during these periods of permanence in physiological environment, cell culture medium. But again, yeah, the main problem was the collagen, basically, in the degradation that we fixed with the cross-linking procedure that you saw.
Okay.
Yeah, there is a question that repeats a bit twice, and it's related to how the structure is built and to the fact that since you have different fibers aligned to each other, when you mechanically test it, you might come to shear between the different fibers and to some wear. Did you observe this?
Basically, yes, we started to observe some shear, and basically it depends from it of course change or depending on the different materials that you use. For example, nylon 66 has a higher shear, but less shear stress, and in the case instead of polylactic acid and collagen 1, or also according to the cross-linking process that makes additional links between the molecules of collagen, we increase the shear. So basically, yeah, we noted that we are start to working how to quantify that properly also during the mechanical test that we are performing. And but yes, some shears, we find some shears inside the different nanofibers and the different materials.
Okay. Another attendant asked about the viscoelastic creep and stress relaxation properties, no? If you, well, what about the creep and the stress relaxation properties?
Okay. Basically, as you can see, our polymeric, we are speaking about polymeric materials, so creep, the creep and relaxations are of course visible in our material. We are starting to explore also these properties concerning future possible application for DVC imaging and studies that we want to carry out. And so we found some creep and relaxation. We didn't actually compared in deep with the one of tendon, ligament, fibers, fascicles, and structure, but we are working on it. And of course, in the next future, you for sure see all the different comparison. But of course, according to the fact that are polymers and polymeric materials, the viscoelastic properties are intrinsically present in these materials.
Okay. Well,
there is another question regarding 3D printing. If you see any role of 3D printing within your project?
Oh, maybe yes. In future study, why not try to thinking about that? For example, to simulate some attachment with the tissues with the bone or something like that. Of course, we have to investigate any possibility. Additive manufacturing and electrospinning, I think, are one of the most challenging manufacturing technique for the next generation of scaffold for tissue regeneration. So, of course, why not? Even because electrospinning works very well to regenerate soft materials, but for the hard one, we need something more.
Very good. There was another question. What about the role of the external layers of the microstructure in also minimizing shears with surrounding tissues?
Okay. Of course, the Electrospun membranes are made of mostly randomly arranged nanofibers. There are a lot of studies concerning the role of prevention of friction and so on of Electrospun mats. So basically, the property to reduce the friction is quite already explored in literature, also in vivo. And what we found also interestingly, as I saw in the slide in which I show you the different orientation of the cells and modification of the morphologies, is also that thanks to this, for example, in the PLA and collagen blend, we can find, according to the fact that we have the same materials in this case for the membranes and in the internal bundle, we can also find, for example, thanks to the cross-linking, the possibility to link in some way the internal bundles and the external membrane, also transmitting different loads to the membrane itself, allowing also to the cells to change their morphologies and shapes. So I think these membranes are quite innovative and quite flexible. And concerning the friction, this is quite widely explored in literature, the role of the anti-friction role of these Electrospun materials, also for tendon and ligament application, of course.
I think one last question from the participants is if you can comment on the cyclic and dynamic loading and cell viability and the mechanical loading.
Yeah, of course. Yeah, as you can see, maybe I can skip going to the last slides if I can. Just a second. I can try if my system works. Okay. I can show you here. Okay, basically the most relevant study that we did about cyclic test in bioreactor is this one. And what we saw basically is that we tested the scaffold for 1 week basically inside a bioreactor. But what we saw is, for instance, that the scaffold were able to resist without any problems inside the bioreactor and cell culture medium during the cyclic tests. And what is very interesting, as I started to answer maybe in the previous answer, is that these materials concerning, in this case, the PLA and collagen, are so flexible, and after the cross-linking, they allow us to link also the membranes, Electrospun with the internal bundles, and allows to transfer also the cyclic loading to the membrane itself, driving the cell also modification. Have a look here, for example, in the comparison of the static loading, in which we have the cells that are basically more or less circumferentially arranged in the membrane, and this because after the immersion and the culture medium, the internal bundles become full of culture medium and enlarge them, generating circumferential stress on the membrane. After the cyclic test, what is very interesting is that the membrane is very able to transmit the axial loading of the testing machine, transmitting this preferential axial load on the cells. And as you can see here, after the cyclic loadings, the cells are able to completely change their shape and start to be actually aligned with the scaffold. So basically, I think it's quite flexible tool, this hierarchical structure, to manage also cyclic test and cyclic loading to resist to cyclic loadings.
Nice. A follow-up question: how do you do the seeding of the cells in these structures? Are the cells only outside, or do they manage to go inside?
No. The interesting thing is that we seeded the cells from the top of this a hierarchical structure that, for instance, was quite very long because they were not chops, but a scaffold of 90 millimeters long, so very long. And we see that just the cells on the top surface of the scaffold, but after the cultures, cells are able also to filter inside. And in fact, in this square, you can see the internal bundles. Okay, for reason of time, maybe it was not probably really clear. And you can see that the cells are able also to filter inside the scaffolds and growth on the aligned bundles, aligned nanofibers inside. So basically, they are able also to filter easily inside the porosity of the membrane, the micrometric porosities of the membranes, and the growth in the whole structure of our scaffolds.
Maybe with the help of some collagen, no? Or the cells are in the PBS, no? Or probably in the medium that you are using.
Yeah, of course, yes. Also, the collagen have a very important role because increase the biomimicry and of the overall structures, but also basically what helps to better filter inside the structure is also the porosity of the Electrospun membrane, that of course is higher compared to the one of the internal bundles, because we have higher level of pores according to the randomly arrangement of the nanofibers. So of course, changing the materials, changing for example also the arrangement of the nanofibers, making them more aligned or less aligned. We can also tune the levels of compacting, also of the different bundles, so we can basically decide also how make easy to cells to filter inside, also according, for example, to longer times to remain in the body, or for example for prosthetic application compared to regenerative one. So tuning with all the parameters, we can basically make possible to cells to do what we want. Of course, with increasing the level of our known about these scaffolds.
Okay. Okay. So I think we can close the session, Sara.
Yep.
Yes, there are more questions in the chat, but I think it's almost time to close this part of the session. Okay. So thanks, Alberto. Virtual applause to you, and of course to all the other applicants, and also to the two runner-ups, Antoine and Mirko, that they will they record the videos and they will be online on our channel in a few weeks, in the next weeks. Okay. So thanks a lot again, and well, of course, thanks. I don't remember if I said this. Thanks to the Enrico and the student committee for organizing this session, and for testing the GoToWebinar platform and everything.
Thank you very much, also from my side.
Okay, thanks, Alberto.